The Tsiolkovsky rocket equation is an equation that outlines the relationship between acceleration due to the exhaust velocity as well as the final and initial mass of a rocket. The equation is as follows. The change in velocity of the rocket body is equal to the average exhaust velocity times the natural log of the initial mass over the final mass. This equation applies the law of conservation of momentum to specific vehicles called rockets. A rocket is defined as any projectile that can be propelled due to the expulsion of mass. The law of the conservation of momentum states that the total momentum of any moving system remains constant. Since momentum is equal to mass times velocity, any mass ejected from the system with an outgoing velocity moves the object in the opposite direction. We can model this with the following equation. Mass initial times velocity initial is equivalent to mass final times velocity final. In order to derive the rocket equation, we must consider this equation and how it relates to what processes a rocket undergoes. A rocket has a payload and a fuel source that makes up its weight. This fuel source is ejected with a certain velocity, propelling the payload at a now higher velocity. In a rocket's initial state, its mass is equal to the mass of the payload plus the fuel source, which we know will be absent in its final state and therefore can be written as the change in mass. We will set the rocket's initial velocity to represent the velocity of the equation. The final mass of the rocket is now equal to the mass of the rocket without the change in mass, and the velocity is equal to the velocity plus whatever change in velocity has occurred. To complete the equation we must derive, we simply plug in the values that we have determined into the conservation of momentum equation. However, we must keep in mind that in order to account for the entire system, we must include any fuel that was ejected. This fuel's mass is the change in mass, and its velocity is the initial velocity minus the velocity in which the exhaust travels. We can now multiply both sides of the equation in order to determine the initial and final momentum of the system. After simplifying the equation, we now have a separable differential equation. In order to set this up to integrate, we first divide both sides of the equation by the mass of the payload. After this, we set up the integration with our bound set as the initial and final values of the variable of integration. We then integrate both sides of the equation. Since the velocity of exhaust is a constant, it can be brought to the outside. By the rules of logarithms, we can simplify the subtraction of the initial mass from the final mass into a division of the two masses. After simplifying, we are left with Tsiolkovsky's ideal rocket equation. Now, how can this equation be applied? For this example, we will try and find the mass of a rocket's fuel to the mass of a rocket's payload. To do this, we must find the velocity of the rocket and its exhaust. Let's say we wanted to send a rocket into Earth's orbit. What would be its required velocity? In order to answer this question, we need to know how far from Earth we wish to send the rocket. The closer you are to Earth, the faster the rocket must go in order to not be pulled down by Earth's gravity. For our example, we will use the speed that would be required to enter the same orbit as the International Space Station, which travels at 17,500 miles per hour. After converting this to meters per second and plugging the value into the equation, we see that in order to solve for the initial mass over the final mass, we must find the exhaust velocity of a rocket capable of entering this orbit. From what I've found in research, this value is typically 2,900 meters per second for rockets heading to the space station. Now all we need to do is solve. First we divide both sides of the equation by 2,900. This leaves us with 2.7. After raising e to each side of the equation and plugging this value into the calculator, we find that for a rocket to enter the space station's orbit, it needs a ratio of its initial to final mass equal to 14.9 to 1. If you want to find what percentage of a rocket's mass is the payload, we simply set the initial mass to 100%, then divide by 14.9. Leaving us with a value of 6.7%. That means that a rocket heading to the space station is 93.3% fuel and only 6.7% payload and rocket body. How accurate is this prediction? In order to find the accuracy of the rocket equation, we can compare it to the SpaceX Corporation's rocket, the Falcon Heavy, when it is equipped to send people to the space station. The Falcon Heavy has a dry mass of 22,000 kilograms and a fuel mass of 433,100 kilograms. That means that its payload and rocket body make up 5.1% of its total mass. When compared to our prediction, the predicted value has a percent error of 31%. It is important to keep in mind that the rocket equation only applies to an ideal situation and fails to account for a number of factors such as air resistance, change in atmospheric pressure, and imperfect nozzle spread. Despite these imperfections, Tsiolkovsky's rocket equation has been used by agencies and space corporations around the world for decades and has made space exploration what it is today.